So we have now related potential difference to current, and we've talked about the resistance of individual objects. We're about to put it all together into Ohm's law. But one of the things that we want to do here is to actually bring batteries back in. For the last couple of videos, we've been thinking about charge flowing off parallel plate capacitors, but it's actually a little more helpful to think about batteries. So remember that batteries have two terminals, and we're going to say that we get a potential difference from the negative terminal to the positive terminal. And we're technically going to call that EMF, curly E, but normally we just directly say that we have an ideal battery where EMF, or curly E, is the potential difference across our batteries. So that means that we're holding that value fixed. This is a property of the battery. And that's true if our battery is ideal, which we're always talking about. So at this top terminal, we have potential energy. So we think about our little charges now having potential energy, and as they're moving through our object, which has resistance, their potential energy is decreasing. So there's a few things to think about, right? If once they get back down to the bottom, they have zero potential energy, where did their energy go? Remember that current here is conserved. So whatever current you have at the top is the same current you have at the bottom. So if that's the case, this isn't kinetic energy, right? Because if it was kinetic energy, you would have charges going at different speeds, which would impact current. So if it's not going into kinetic energy, because we can't really talk about our charges speeding up, but we see that we have actually had a big change in potential energy, where did it go? Well, let's remember back to our energy model. We said that there's potential energy, there's kinetic energy, and those are conserved if it's non-dissipative. And one of the things we learned about, one of our dissipative forces, was friction. Remember here, we said originally you have to have an electric field for current to flow because you have to overcome the resistive force of colliding our charges into the ions that make up the metal. So what this means is that your potential energy is going into dissipative energy, right? It's being dissipative. And so that's like friction. Well, where did friction take our energy to? It took it to heat. It turned it into thermal energy. And remember that when we first started with current, we said that one of the indicators that a current is flowing is actually the wire getting warm. So I promise this whole thing makes sense, that we see that we're losing energy, that our charges initially have potential energy, that by the time they get to the bottom, they don't. Where did this energy go? It went into heat, which makes our wire warm, which is one of our starting points. So where we need to then say is, okay, we know that there's a current, but how much current? So that isn't actually going to be controlled by the battery. Again, the battery gives us our change in potential. This wire, which has some length and some area and some material, means that it has some resistance. So the resistance of our wire is actually what controls how much current flows. The current that's going to flow out of the battery is given by the potential difference between the two terminals divided by the resistance of our circuit. In this specific case, it's just of the wire, but we're frequently going to put other stuff in the way. There's going to be resistors, there's going to be other things. So note that in this case, we're not assuming an ideal wire. We are actually saying that our wire has some resistance, and we're going to talk about this distinction in a little bit. But this is really tricky, and I find students get tripped up on this. The battery is willing to give you, in an ideal scenario, however much current you demand from it. And how you are demanding current is by changing this resistance. So this is from the battery. It's fixed. This is from the circuit, whatever you're actually attaching to the battery. And this is then just what results, what is necessary to make those other things related in this lovely equation that we call Ohm's law. which again, you've possibly seen in a previous physics class, and you've possibly seen it written V equals IR. So that's all we're doing right now. So Ohm's law, we're going to frequently write the equation this way, but you can obviously rearrange it in different ways. But the nice thing about this is that it's saying current results from these two things. Again, delta V being a property of your battery, R being a property of your circuit or whatever object you're talking about. So the current through your object is proportional to the potential difference across the object. Right now we're thinking about a single object and a single battery, but that is going to get more complicated. If you remember back to capacitors, we found a way to make equivalent capacitance, and we're going to need to do the same thing here as we combine more circuit elements together. So there's this proportionality constant, which is resistance. And so one example of this is we can make a plot, and we can plot a circuit where we've put different potential differences across, something. And so we're putting different delta V's across it. You can think of this as being due to a battery. And then we're seeing how much current we get flowing through it. And it more or less follows a straight line. There's going to be a little bit of variation due to just experimental uncertainty. How good are you making your measurements? But you get this straight line. Notice that it goes through zero. If I put zero potential difference across something, I don't get a current flowing. But then otherwise, it follows a line of best fit, and my slope is given by 1 over R. As you should be able to see from Ohm's law, this is like saying y equals mx, where y is I, right? X is therefore your delta V, and this is then your slope, which is 1 over R. So all Ohm's law tells us is that you have a linear relationship between current and potential difference. The proportionality constant is called resistance. Only some objects follow this. Now, what's confusing about this is that we're really only going to study the objects that do follow this. But it's important to note that this isn't true for everything all of the time. So one obvious example that doesn't follow this is a capacitor. If you put a capacitor in your circuit, you can't actually just define the resistance of the capacitor. It's really confusing to actually talk about current and potential difference on a capacitor. It actually depends on time and the charge. So capacitors don't follow this. Batteries also don't follow this. If I connect one battery to another battery, weird things happen that are definitely not governed by Ohm's law. There are other components called solid-state components, like LEDs, that are not ohmic. They do not follow Ohm's law. So Ohm's law works really well for things we call ohmic, for things like resistors, and that just means that it has a linear relationship between current and potential difference. The slope we call resistance. Non-ohmic materials, like a diode, you have not a straight line. So what's tricky is it doesn't really make sense to ever talk about the resistance of a non-ohmic material like a diode. Yes, you get a slope for any point you're at, but the slope is not always the same. So mostly in this class we will focus on ohmic materials. We can talk about them very easily. You have to use some more advanced techniques to talk about non-ohmic materials and how they behave in circuits. And if you're interested in that, Physics 240 goes into more depth into that.